Hi everybody, welcome back to my channel, and today I would like to continue the discussion that we started a few months ago about using numerical integration in practice and in a project. I think we started with how to use a numerical approximation of function derivative, and we ended talking about numerical integration, but I don't remember we had enough time to dig a little bit deeper into that specific topic. That one is so important because, for example, right now I'm trying to implement an experiment in which I need to compute the integral range of an experimental covariagram model, and that is, let me show you what that is. So this one is not a covariagram, this is a variogram model, and the explanation is still the same. So to have the value of that integral range, what you will do is, for example, let's take this curve. Okay, this curve model. I wanted to say curved line, but that it sounds weird. So let's say curve model because okay, let's say curve. With this one, what we call an integral range is you will compute the area under this curve and divide it by the seal of this model. So the seal will be a line that you will plot from this, let's say for example, from this point to the end, and that line is touching your curve but without crossing it, so it will just slide on your curve but without crossing that curve. It will be tangent to that curve, and the result is, so if you take the area under the curve and you divide by the c, the result is what we call the integral range. So we use that value in so many different cases because what you probably know is that it gives you some information about the the spatial domain in which you will observe the greatest variability within of your random function. So you will use that differently depending upon the, let's say, the model that you use to feed the, okay, the theoretical model that you use to feed your experimental variogram. So I think we have some example down in this file. Okay, by the way, thank you to Xavier Miri. This is one book that he produced, and it's so important for every level. If you are a beginner, then you should read this book. But even when you have done, like, let's say 4 years of geostatistics, you still need to read this book sometimes because it really includes so many information about linear geostatistics, and once you have those information, that I really believe you can do almost everything in geostatistics, even when you have to face some non-linear um, trend or behaviors. I wanted to show you some example, but I felt like it's somewhere. Oh yeah, I think it's here. Nope. 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 It's not here. Let me see. I think there is a table somewhere here. Anyway, we will talk about that one another day. So today I really wanted to focus on this. So you need you need to compute the area under a curve or a line. Technically, this is an integration. This is running the integral of a function. Like, let's say this one from 0 to 1 is computing the area of f of x under his domain. So under the different values of x from 0 to 1. So this is basically what you are going to do in that particular case. So now the question is how you would do that in your computer, because I believe when you're using some observations, or let me say a sampling of your random function, it is not an analytic. That word is so hard to pronounce some days. Uh, it is not an analytic function that you have and you will replace x by a value. It is really something like you have a location. Let's see. In my case, for example, I have a location represented by, let's say, a x coordinate and a y coordinate, and I have a value which is the real sampling. So like an observation of that random function. So you don't have an analytic representation of that. You really have just the values, and how do you do to use the values and have your numerical integration. So this is what we are talking about here. I mean, this is what we started talking about last time. And today I just wanted to show you how you would do that. So you will basically have to resample your domain. So to resample means that, let's say you have 10 points, but you believe 10 points are not enough to compute the area on your curve. So you will try to interpolate between the 10 points so that you have more than 10 points. Now, the fact that you are modifying your observation and you will use an approximation of those of your observations using an interpolation will bring a bias in your study or in your experiment, but it's okay because this is what we do in numerical analysis. You will almost always have to deal with biases, and it's not bad as long as you give information about the entire process. So what you did when you decided to run the interpolation between your observations, and what you believe will be the error or the bias of what you did. You need to provide those information, and once you do that, then you have nothing to be afraid of because you provided information about your experiment. So this is what we're going to do in the coming videos. I think, no, I don't think. I did it 3 years ago or something like that. I tried to compare the Simpsons rule with what MATLAB would provide as a numerical integration. So I did the Simpsons rule in C++ and tried to compute something like, where is it? Something like this, but with the Gaussian function here. Because I know that for a Gaussian function, if I change this, for example, so if you take the normal distribution and you take the PDF of a normal distribution, you can guess the value of a real normal distribution just with the table. So meaning if you take one value, you can use the table to guess this. So to guess something with the density function. So that is what I did. I took that table and I used MATLAB to see if MATLAB would get closer enough to the value in that table, and MATLAB did. Okay, MATLAB is so great in numerical analysis. Okay. Then I tried to code my own juice, I would say it like that, so my own product, my own thing in C++, and then it compared with what MATLAB gives as result, and we basically have the same value, meaning that not only the Simpsons rule is great, but also I can do that in C++. So I will do it again because now I needed to be somehow flexible regarding the data that you will provide as your functions argument. So see you guys in the coming video, probably the next After this one, the next video that I will upload will probably be that video. See you, stay tuned, and have a good day or have a good night. If I mean, depending on what time it is when you're actually watching this video. Bye.